Hey there.
Good afternoon.
Can you hear me?
I can hear you. Can you hear me?
Hello.
Oh, can you hear me? Oops. Are you able to hear me?
Hello. Hi.
Can you hear me?
I think something is wrong. Audio is not working. So I am going to check out what's going on. To test the sound. Hello, 1, 2, 3. Audio is okay. It was broken. Yeah, now it is fixed.
Can you hear me?
Yes, I can hear you now. So this was basically me muting my machine because it was like playing loud music and I muted and I forgot. That was happening. So now I am speaking. You should be able to hear me, and I'm able to hear you. You should be able to see me, and we should proceed. So there we go. Starting to project my screen again, and connecting to that remote computer where I have the notebooks running, checking whether the notebook system is actually functional, and then opening up Firefox to get to that notebook section where we, oh, not this Chrome box. And so that's, by the way, here is what we were doing the last time was chapter number 4. And the thing that I was playing around with was this notebook in OneNote, where I have that book opened. And in here, I was the last time dealing with, and that's the hard part with this OneNote thing. It's so hard to actually keep track of as to what is going on, because the entire book is a one page in OneNote. That makes it really unwieldy. And so I split into 2 parts, like 1 through 7 and chapters 8 and later on, but that still doesn't help. Like split the book into 2 parts like this, but it still doesn't help at all. It is still unwieldy, and that is something that I want to overcome. So I will do that, by the way, in this way. What I have done is basically split the notebook into separate chapters like this, the actual book itself. And now I can scribble and do whatever I want effortlessly in here. And this is a completely different software as opposed to OneNote. OneNote I thought will be nice and useful, though, so I can share it with people who participate in the program. But apparently, there are gotchas in the way OneNote works. So I would rather have a system to share this handwriting with you, but apparently that doesn't work exactly the way I want this OneNote to actually function for me. And so even right now, you can see that it's sometimes difficult for me to erase portions of this. So the erasure or the eraser just disappears. I want to erase this marking and I cannot. So that is the stupidity of OneNote. For some reason, it doesn't seem to work the way I want. And now you see that is stuck. That is the horrible nature of OneNote. So I'm going to eventually switch to this Notability toolset that I used to be using for so many years. But I thought for the book, I wanted to use this new method, and it doesn't work exactly the way I want. So I'm going to skip it. But I have all my notes here. That's the challenge. So I'll transfer my notes and then eventually move away from my handwritten notes to the Notability system. But for now, we were at the last time we were talking about the database corresponding to flowers. And that was in chapter number 4, if I remember right. So I'm heading there right now. So this is your flower database, I think.
In 4.
Mm-hmm. And so where is the flower database? Okay, is that the flowers? Maybe not.
I think
We're
it's
just
on the other way.
So let me just go to the point where we were, and that I think I have notes in the session here where it tells me where exactly I was, and so that's where I'm heading. Is this fall 2018? Videos will tell me where exactly I was. So just before the iris data set, that's where we were at the last time, chapter 4. So this is chapter 4, and let's get to the iris data set now. So iris, come on, iris. The flower database. It's a good database, by the way, and so that's what I'm heading towards. Yeah. Flower, come on. And that is not, the hard thing is I have to like scroll multiple pages to get to the point where I want to get to, and that is so lame. In fact, that's the reason why I will probably by next couple of sessions, I'll discard this OneNote thing completely and rewrite my notes on there comes the iris database. So this is what I want to talk about. Now here, the underlying idea of the data structure, I think we briefly discussed that, but I would like to quickly recap that idea here, is the underlying concept in this data set is actually beautiful. I will describe how it is beautiful in a way that will help us understand what we are going to deal with. So there are apparently these 3 types of flowers, and I am bad with biological names. So I'll just call them a flower called S. There is a flower called, let's pen size, it's too big. Yeah, so there is a flower called S, and then there is a flower called V, and there are 2 V's, Virginia and versicolor. So yeah, those are, so this is silly. So these are the 3 flowers. Let's call them with simply A, B, and C. That's easier way to handle that. And so that's the naming of flowers for me to just repeat: iris setosa, versicolor, and virginica. Those are 3 flowers of the same family, apparently. And so they differ from each other in various ways. And so in this picture, as you can see, there are these 3 types of variations of the same flower. And what the database that we have, actually, there are so many data points that we have collected in the database. And the database has petal length, petal width, sepal length, sepal width. Those 4 metrics. And along with that, we have a label. The label is basically telling us which flower is that. Is it A, is it B, or is it C? Like that. So for whatever values we have in centimeters, all the data points for various number of flower items, data items are called instances, various data instances, we know we have a labeled data. Labeled data will tell us whether it is a flower A or a B or a or a C or what like that. So that's the data set we have already. That's what we are talking about here, is in this picture. If you look, and I will draw now in a color red. And in the red color, you will see that we have length, width, petal length, petal width. And then these 3 colors corresponding to A, B, and C are the 3 flowers. A, B, and C are the 3 colors, red, green, and blue. So here are the red items, the green items, and the blue items. So basically, it's a scatter diagram illustrating the entirety of our data set. That's the data we are dealing with. Now with that, just some biological references here about what is sepal and what is petal and all that. For those of you like me, I don't know. So I have this picture to help us with that. And that idea is simply this thing, the green item here, the back of the flower, that apparently that thing is called sepal. And the red item here, the colorful item, even green is a color, but I'm just saying the front item on the face, that this thing is a petal. And what the calculations, the data sets actually represent is the length of the petal and the width of the petal, the length of the petal, width of the petal. And they have calculated and actually measured various lengths and widths of petals and width and length and width, like that, length and width on a variety of different types of flowers. And that's the database. So what we need to be able to do is, with that data structure in hand, we will use a variety of machine learning techniques to learn what would be a flower given petal length, petal width, sepal length, sepal width. Given these 4 metrics, are we in a position? So we basically go out in the wild and grab a random flower, either it is A or a B or a C, we don't know which one it is, and so we want to measure it. So we'll measure these metrics on any of these random flowers we pick. And we pick only from this family, the iris family. And that's the iris data set. So we'll randomly go out in the wild, pick a flower, measure the values here, 1, 2, 3, 4, and then apply it to the algorithm and ask it to predict. It should tell us correctly whether it is A or B or a C in the family. And that's the underlying concept. We'll train algorithms based on the data that we have, which is this data set, and then find out how we can use the ideas in a variety of different algorithms to come up with this prediction. Like, given data points, tell me which flower it is. That's the prediction we would like to make. And so that's the underlying idea. With that, I'm erasing the red markings and proceeding to scroll. And when I scroll, I will actually move this on the side. And yes, that should help. And this should also help. Okay, so with this, the underlying concept that we want to focus on is, let's say we begin with only 2 parameters. So the 2 parameters I want to focus primarily on are these guys. Let's say petal width feature, just the petal width, only this feature. That's the first segment here. Yeah, so we are just grabbing only one feature set called petal width and just working with that in our hand. So that's going to be detected only on one input feature, that is width of the petal. And based on that, that's what we're doing here. We import the data set, and then we have, let me scroll a little bit before I start writing on this. So scrolling, adjusting this, and then annotating. So we import the data set here. Then we load it, and then we list what do we have. And we get, data, target names, feature names, target, and description. And with that understanding, what we are doing is, evaluating X as the petal width and Y as the answer to the correct type of flower, whether it is A or B or C. And so in this example, what we are doing is, if it is a iris virginica, which is I think C in our definition of A, B, and C, it'll assign 1 to it, or otherwise it'll put a 0. And that's the iris virginica or not decision. That label, we have modified our label, and Y is the value, which is basically a derivative of the actual target value. These targets are already defined here. Target labels are the labels that were, A, B, and C, or, virginica or not. So based on whether it is a C, so this was A and it is labeled as, labeled as A, then it will be a 0. If it is B and it is not A, that means it is also 0. But this is C, so this label will be 1. So we're creating a Y value based on target values, whether it is iris virginica or not. And that's the a new array we are creating here called Y. And that Y values will be zeros and ones based on whether it is that particular flower or not. And that's our subset of the entire data set. And then we will just simply do a linear regression. So that's linear regression. And we do a fit on logistic regression. And then we'll try to estimate probabilities for a flower for varying petal width varying from 0 to 3 centimeters. And so that probability distribution is what you're looking at in this picture. So if the petal width is somewhere in between this line here, below that, if it is in that direction, I mean, it is less than 1 point some number here, 1.6 maybe. Actually, it is, what's the number here? Let's read that carefully. So I'm erasing my red markings again to reduce clutter and read what the graph actually, read what the markings actually say. So if you look at the data set, you will find that the plot here is being basically drawn based on whether the probability is a 1 or a 0. That basically tells you whether it is a Virginica or not. And that is where the decision boundary is. If it is less than this some threshold number, then in that direction it will be not Virginica, and in that direction it will be yes Virginica. That's how the probability calculations are estimated to be based on the data set available only for one this feature, and the labeled values we have either it's a 0 or a 1 based on whether it is that particular flower or not. And so here is your probability distribution based on just one feature, and that's what we see, and we find that this is the threshold that turns out to be the actual value. Now in reality, what you will see is that the distribution is not exactly at this red line where it stands. Probably it stands at say about 1.6 or something like that, 1.6, 1.7, some number like that. Whereas there are flowers with 1.4 width that are also yes Virginica. And it is this decision boundary is actually not exactly correct. So I just wanted you to know that we are making this assessment based on only one feature. And that is the reason why the decision boundary is a little bit off than what the actual values in the data set. You will find certain flowers that are actually Virginica are not above 1.6. They're actually below 1.6. Like some cases of 1.4 are also Virginica. That's what you will find. In fact, here it tells you the petal width of Virginica ranges from 1.4 to 2.5. That's the range. So between this number and between this number. So these two numbers is where the actual flowers belong to the Virginica family. Or rather, I should say Virginica species of the iris family. And that's the finding from just one, what I would call feature, which is this one. So erasing the red markings again and scrolling now. And what we are really trying to do is this decision boundary that we have at about say 1.6, like we discussed earlier. This decision boundary 1.6 is basically the point at which both probabilities on this side as well as this side are at 50%. So that is how you will use this classifier to predict just a lame single feature classifier that predicts whether it is Virginica or not. And that's the decision boundary that we try to find out. The underlying concept behind this decision boundary is basically to be able to segregate in something like, I draw my decision boundary like this. So anything below that, let's say like this, anything below here is some X and the other value is not X. That's the underlying concept. So we are drawing some boundaries in a data space. So this was a linear example. And so the linear boundary representation was basically this central line where you divide it by 50% here, 50% there, and yes or no. That's the idea from a linear standpoint. And you can see if you have all the data points plotted, they just are plotted like these data that are not and not, whereas these data points, they are yes, Virginica. These are not Virginica. You see the decision boundary is kind of overlapping here and overlapping a little bit here. This one is kind of clear with the third type of flower, which is not, absolutely not Virginica. And so that's just one-dimensional expression of a decision boundary is how you will begin to decipher between this or that. And if you add more features, the lay of the land becomes a little complex. Like for example, in this picture, when I'm drawing something like a two-dimensional picture representation of a boundary here, which is artificially drawn line. It's not a line, it's a curve of some sorts that basically separates these guys from these guys. And so on one part, it is going to be a yes, on the other side, it will be a no. No, not that flower. So that's the underlying concept. Now, if you add more variables, the representation of this doesn't remain in a 2D space. So it will go into 3D or sometimes even more higher dimensions. That is very, very, likely to happen when you have more features and more dimensions to it. the visual representation is very hard to actually draw on a screen or a piece of paper. I think you already understand that piece. So let's go forward, and we will add now two features. So the two features we'll be adding are specifically the petal width and petal length. So that feature representation, we are now incorporating these ideas, extending the same concept we discussed. And what we are looking at is this representation, which includes this and this feature. So two features. And based on petal length and petal width, if you try to plot a graph of all the flowers, which are basically here, a decision between whether it is a Virginica, yes or no. That's the decision point. Basically, that's what we are making. And we plot that, and we find what we find is that there is this line here, which turns out to be a decent decision boundary. And that's the underlying concept we are trying to draw on a piece of paper to understand whether the two sets of yes and no, Virginica, yes and no, are they linearly separable? If they're linearly separable by just drawing a straight line like this, then it becomes easy to handle those things. And so the underlying concept is that these models that we are looking at, when we have a linear decision boundary, it's basically a pure, simple black and white decision-making system, when we can just quickly tell. And by the way, if you zoom into this chart a little bit, and if you go look at the chart itself, but a little deeper, so I'm going to scroll this up and actually zoom the picture. And so that's what I'm trying to do. If the thing responds to me, yes, it did. So if you look carefully, and I will now use the red marking again, one more time, is the red marking coming up. And you will find here that these green items, these green dots, they are yes, Virginica. And that green dot is here as well, and is here also. And is, of course, here, not there, but here. And so those green dots are not succinctly divided by this dashed line. There are some points on the other side of the line also. And similarly, these squares, which are indicating of not Virginica, no Virginica, these blue squares. If you see the decision boundary, it is crossing over to the other side. There is a blue square, there is a blue square here, and that is basically a lack of clear distinction between yes and no. And that is what makes that line ambiguous. It's not clear decision boundary. So we have to handle those scenarios in a fashion that will basically help us decide whether it is this or that. And based on that, we can then, of course, improve upon how we are handling the data, and of course, include all these other metrics and come up with a better model and a better algorithm to actually very correctly predict, given these numbers, 1, 2, so whatever numbers we have, some number here, some number here, given these 4 metrics, we want to say, okay, that is which flower. And so they can just tell us A, B, or C, whatever that flower type is, that based on these numbers input. So this is the input, that's the output. That's what we are predicting or going to predict once we have a proper system in hand. What we want to do is that this underlying, so let me adjust my screen a little bit back again. And so we were looking at the picture. I'm going to shrink it back to the way it was. And what we will now do is look at another type of algorithm, basically, that predicts not just one answer, but, so let me describe that a little bit. So here you see that we are limiting ourselves with just one feature, and that was an input, and we then limited ourselves to only one output, which is basically a yes or no output. That was the thinking that we have been up until this point, where we said, you know what, whether it is a Virginica or not, yes or no. So we reduced our labeled data set into a narrow one-dimensional space. But what if we want to actually predict that we want to have multinomial responses coming as an output, meaning it should be able to tell us whether it is Virginica or the other 2 flowers. So I just forget their names all the time. So yeah, just A, B, and C, 3 flowers. And so Those are the 3 powers we should be able to predict. So that requires multi-class output, output that will say yes, no, no, something like that. That will represent a output that is a multi-class output. And so the discussion we have had up until now in the logistic regression, that doesn't support that scenario. So we have to have a generalization made to get an output that will be a multi-class output. That's the underlying concept. And that's what we are trying to build towards. And the method that allows multinomial regression, multinomial logistic regression that outputs value of 1, 0, 0, for example, multiple outputs, is called softmax regression. That's the name of the regression technique that we will be using. So if you now focus on this different technique of making a multi-class output, what it does is it will calculate basically the thing is known as softmax score, or you can call it, think of it as a cost function, if for all practical purposes. And so let's understand what this technique will help us accomplish. And so without going into these specific concepts about what they are trying to communicate, first let us understand how does this thing actually work from a user's standpoint, and we'll go into the math later on in just a few minutes. But if you look at the math is of course increasingly going complex as we go along in deeper and higher order algorithms, and that is, by the way, coming all the way up through 7th or 8th chapter. There is too much math, and so the math is, we'll try to keep that in control and not drown ourselves in too much math, because it can get dry and boring. I would rather keep this discussion at a point where we can put these to use, and that's what I am really focusing on. So I want to keep that thing also open. So the notebook we should also have our 4th chapter where we were running these things that we want to be able to run. They should be available for us in the softmax regression example should be available to us. So I'm just trying to find it. I think this is where the data set is. So let's begin with loading that data set. Where is that data? Logistic regression. And then here is the data set to load, Iris. So let's load that. And here I'm going to load the Iris data set quickly in this section. Here, importing data set Iris. And then print out its description. And the Iris plants database is basically contains 150 instances with 4 numerical. Hold on, what is this noise? 4 numerical attributes, and the attribute information are sepal length, width. We already discussed that, and there are 3 classes: Setosa, Versicolor, and Virginica. And here are these summary statistics available to us. And this database is available from a university of some, I don't know what that UCI EDU is, some university. And also the person who donated that is from NASA. And this was originally created in, I think, by this person, R.A. Fisher. You can find details on Wikipedia. But let's go read on what the next steps are. So here, what we are doing is just focusing on just the one metric called petal length, and also associating the Y values corresponding to the targets and limiting them to 1 if it is Virginica and otherwise 0. So basically narrowing down that. I want to run that step. We already discussed that. And NP is not defined because we apparently haven't loaded a library ahead somewhere up on top. NP here is not defined. We should go up on top. And where is NP? Here, import and numpy as NP. That should handle it. Oh man, something else is not defined. And that happens when you just suddenly start a notebook in the middle of the game. That's not the idea. And underneath, so I'll go on the top and just quickly run through these guys. So we'll keep running. This should be fast. I'm just going through, zipping through these and just reaching the point where we want to be, which is logistic regression, and then the iris database comes along, and then our sklearn. Okay, and now it is running. So this is the graph that you saw in the book also, which is what you noticed, that this graph here, the one that shows you decision boundary in single dimension, that is what the figure in the book is actually a little bit fancier, because they have, matplotlib has output more parameters to illustrate the picture better. And if you now draw that picture, I think we'd already discussed that, so we can move forward. Now we are talking about understanding the decision boundary function, which is basically mathematically calculated as the point on this graph, which is 50% yes or no decision making point. That turns out to be 1.61. And in the predictions for values of 1.7, 1.5, if you put a 1.7, of course, it will give you a 1 to the flower type, saying, yes, it is that type of Virginica flower type. And if you give a value of 1.5, it will give you a 0, meaning it is not the Virginica flower type. So we already discussed this. Now let's keep forward. And now what's that error? Value, so X is not loaded apparently. So we'll go back one step. Now what? What did I just do? Why is it erroring out? Okay, but jump a bunch of steps back in space, in time here. 1, 2, 3. And now please show me no errors. Yes, nice. Next one. And then logistic regression with petal length and petal width, 2 of the items together. And that worked out okay. Now let's read what we have in this segment. So you will see what we are doing. What we have taken is, again, using logistic regression, but this time with petal length and width. So 2 features, and that is the idea behind our segment. This is what I hate about OneNote, is these black circles they should disappear, but it doesn't disappear for some reason. And I need to quit OneNote to get it to work correctly. Okay, come on, OneNote, bring it back to me. And there it comes. So here, what we are looking at is, again, that annotation, petal length, petal width. We are deciding this Y variable as something that will indicate the underlying type of the item that we are looking at, type of the flower that we are looking at. Then we are doing a fit on logistic regression with the inputs that we have, X and Y. And once we have that, we are trying to create a mesh grid, basically trying to draw this picture that we have there. And we estimate, I think most of these are plotting functions. So this is a plot function, plot functions, and plot.show to show this figure. That figure shows logistic regression counter plot. And here you will see what we already briefly discussed is the idea of using 2 variables with one feature, basically yes or no, whether that flower or not, Virginica or not. And clearing the red markings. And now discussing the ideas regarding our softmax regression. Where is that one? That's what I want to get to. So this is your softmax regression starting point. So what we are going to now load up is the softmax regression fit on the target values, and we are taking just petal length and petal width. So this indication of 2 and 3 are a portion or subset of the data in X, storing only length and width for petal. And then we have the entire target for Y. This Y will contain a multimodal, or rather multinomial answer, A or B or C, 3 types of flowers, whether it is yes or no. And that's the softmax regression that we are running here. And as a consequence of that execution, we get our model fit. Once the model is fit, we can make use of it. And let's go see how do we put that to use. And so the underlying concept that we are looking at is right here in the book, which is softmax regression fit on X and Y, and then we can calculate predictions on the chances of a particular item being a flower of the type that we want. And that's what you will see in the execution of the estimation of probabilities. So once the model is fit, like right here, in this segment here, which is matching what you have here, softmax regression fit, then once we have that, we can then make predictions. So I think in the next step, we will make predictions. So clearing this and executing that portion, and then making a prediction. First of all, drawing this picture, and where's the prediction thing? Yeah, the prediction card, that's the next thing. So the next thing, let me execute that piece also, and then we'll discuss what we have here. So what we have is a plot that we have drawn based on, again, matplotlib. Most of these are plot functions that plots the softmax regression contour plot. And if you look at this picture, what you will find is it is actually a way to represent 3 different classes of flowers drawn in your green, blue, and yellow background. And this blue and this green and this yellow background are basically representation of the 3 classes that we have. So now with this data and this model ready in our hand, if you try to make a prediction of some input that we provide, and these inputs are again the same that we know that already. We know that we are using just the width and length and width. So this is your 5 centimeter long, 5 cm long length, and this is your 2 centimeter long width of the petal. So just the petal widths we are using right now in this data subset of the data structure, and using that data 5 and 2 to asking the model to make a prediction. What are we looking at? Is it something that we know? So it tells you it is a 2, and 2 basically I think means for the 3rd flower type. So 0, 1, and 2, and that is going to be the flower type of 1, 2, and 3 values of predictions or probability of it being a 0 flower type, it being a 1 flower type, or it being a 2 flower type. These are the 3 probabilities that we have from a predict proba portion of the softmax regression, which tells us that this probability is very low. This probability is also reasonably low, but this one is high. It's a to the power -1, so it's like 94.2% chance that the flower you're looking at with a length of 5 centimeters and a width of 2 centimeters is actually a flower number 2, 0, 1, 2. And 2 happens to be, I think, this one, if I'm not mistaken. But that's, it will answer Virginica for 2, yes. So that is this flower, a Virginica flower, which means it's a green triangle. And so if you now take this 5 centimeter length, so we have 1, 2, 3, 4, 5, it's right here. And the 2 centimeter width, so it is like 1 and 2 centimeter width, so it's somewhere here. So it is that flower. I mean, that point there that we're dealing with. And it is clearly in the green area, And that tells us from a visual perspective that we looking at answer being 2, meaning it is this area, 2 area, or the green color corresponding to the Virginica segment. And that's how softmax regression helped us in, first of all, helping us draw the picture and a visual illustration of what the contour plot looks like, and then helps us predict various probabilities for it being a flower type 0, flower type 1, flower type 2. And this is a very high probability. And so based on these estimations of probability, we can then conclude that the flower is actually a 2, which is Virginica. And that's the underlying concept of using this softmax regression with multinomial output. So there is a thing to remember here, which is that we have 2 different solvers, and so the solvers under the hood that scikit-learn uses they're not, I think I called out. Let me point that out to you. That might help us in understanding this better the next time we run it. So I am stopping my annotations, clearing them, and looking at my notes as to what it makes. So this softmax regression uses the technique of one versus all by default. And we have to set multi-class to multinomial. And that is something that you set pretty much like this in scikit-learn. And that makes a logistic regression into softmax. That's the underlying concept. It switches to softmax regression if you use the multinomial class. That is something to just take note of. If you want to use logistic regression and output multinomial outputs like A or B or C being 0, 0, and 1, that's the output you want. You would expect multinomial output. Then you have to set that parameter like this in your logistic regression calculations. And there are two solvers available here apparently. So this is the use of LBFGS solver. I think we have to read the documentation for scikit-learn logistic regression on their pages, documentation page, to help us understand what these algorithms under what solvers they're using under the hood, and what is the default solver. I think this one is probably the default solver mentioned here, which is something that that you probably will need to know if you're running this particular logistic regression in a multinomial class. I'll also generalize as to how do you find out the details regarding a particular algorithm, and how do you conclude to use which of these parameters. So if you want to just search for this, say scikit-learn and say logistic regression, and then say LBFGS solver, or just search for the available solvers, it will just take you straight to the documentation where it will tell you all the details under the hood about solvers available. So here are some solvers that we can put to use: string solver, LBFGS solver, liblinear solver, SAG solver, SAGA solver, and by default it is liblinear. So various choices available. We have to go and understand these in detail. If you are in that specific, if you are focusing on that segment, of course you will go back and read each and every parameter corresponding to logistic regression in your scikit-learn documentation, and that is what we are looking at right now, which is how you always go back to get to the source as to where this thing is actually coming from, and you should be reading the correct version. There are other versions, like right now we are using, I think, 0.21. That's the version of documentation that we are looking at. There are other versions available, and you can, of course, zoom on to the correct version that you're dealing with and handle that accordingly. So let's go forward. I think this finishes this chapter. There are exercises subsequent to this in the book that you should do. And I think, at some point, once I go through the entire book, I will come back and do the exercises also. I want to do that with you also. So we will, do some of the interesting ones in the book that we have not been discussing specific exercises at all. And I'm leaving it to you whenever you find time. But I'll come back once we go through the entire book. I'll actually bring up specific projects of interest that you can actually apply. And one of them that I saw the other day was an interesting one. I should just point out to you. It's called YOLO. YOLO has a meaning, which you probably know already, but that's not the meaning. The YOLO thing that I want to talk about is actually, it means you look only once. And then you apply, let's go search, you look only once. So that is a project in, where is that? YOLO object detection. So here it is. So YOLO is, I think there is a.
If you write anything on your
computer. No advertisements, please. So bottom line is, this YOLO thing is a deep learning algorithm project in which if you feed a video, it'll tell you exactly which item or which thing or person or object in that video is what it is by looking at a face. Say, for example, so if you look at this video playing in the ad, it will just identify that this is a person and that this is a couch or something like that, and this is a pillow right there, and this is some object that even I cannot detect. That's a lamp. And so that's the underlying idea behind this YOLO, is you look only once, is the underlying concept. And I think there is a good exercise that I want to be able to play with you, and it uses TensorFlow and a bunch of other libraries to include, and you feed a video to it and you play it runtime. It will basically superimpose and say, this is a couch and this is a person. It will label live, and by looking at it only once and just quickly label and identify what object are we looking at. Basically, it's a visual recognition system. And you will see a live example, and I'll play with after we go through the entire book. We'll do a bunch of exercises also. It might need more time, by the way, and I think you and I have already discussed that. So we'll take as much time as needed to make it materially useful to you, and that's what I have already told you. So we'll do that. By the way, if I somehow forget the last day of the program, it is, I think, November 16. So please remind me that I should actually create the certificates and send it to Bellevue College, so that I should not forget that. That's one thing that I would like you to please remind me. I'll do that. And then we keep our program running as we go along. So I hope you understand what I'm saying, because I want to make sure that I produce the certificates for you on the end of the date on which the program ends. I think it is ending in November 16. And the hard part of that is I have erased all the dates, which is the silly thing that I did. But you will see that the site doesn't have any dates anymore because I have new dates announced already. So I removed the old dates, and that is something that is necessary, but yeah, lame. So I had to do that. So I did, which means there are no date references here. So it is just you and I have to remember. And there is a bit, what am I saying? There is a place in Bellevue College. We should just confirm that. Bellevue College. Cloud computing should take us straight to that place where the date should be published. So yeah, I think we are in good shape. So here we have the dates published for the machine learning program, and the dates are November 15th. Okay, that's the date. So not 16th, but 15th. So I will remember that. Okay, I think that's a savior. Because I wanted to have that record, and now we have it. So that's what I wanted to keep track of this date. Okay, and let's proceed. So this is closed. This one is closed. This one is YOLO. And that's your exercise set. So I'm going to close this file and halt it and switch over to number 5, which is, I think, a little bit more interesting set of algorithms that I find a little more interesting than the simple ones. So the new ones that we are discussing here called support vector machines. And I think these are some of the most comprehensive things that you can think of. They're very intuitive in the way you think about these things. And so let's go talk about SVM a little bit. Here is my annotations. So SVM. Think of any kind of, in this picture that I have here, it's a two-dimensional representation of some data points. And we have these dots here and those dots on the other side. I should use 2 different inks. So clearing it, I think I already have used 2 different ink right there. So you see that these are red dots and these are black colored dots. And so the underlying idea behind support vector machines, it might sound weird with no apparent meaning to it. So I'm trying to tell you the meaning underneath this concept of support vector machines. The idea of support comes from the fact that these green lines that you have here, these ones, they provide some kind of think of it as a support. Support to what? Support to the data points here and keep them all on this side of the line. And this support vector, the other green line, is basically providing support to the data points here on the red side and keeping them on this side of the line. And thereby, what I'm really trying to build is a path in between those 2 green lines so I can drive around here. So that's the path. And that's a clearly separable path, right? If I have a system like that, that will let me clearly separate these paths from each other, or these 2 support vectors from each other, That's what I want to do essentially. So from a graph perspective, or purely graphing some idea perspective, if you have data points here that look like dots, and if you have on the other hand data points here that look like circles, and if you are able to find out the widest support boundaries to separate these guys from these guys, that's the area you would like to have. And you will find that this path in between is kind of wide to the widest possible extent. And that is the underlying way of thinking, that these lines are providing support and keeping the data points there on this side and there on that side, and find a way to optimize the width of this. How wide can you go? That's how the math will operate, to help us draw these lines on a graph with data sets that will basically help us in either classification or regression or outlier detection, all of these. So that's the underlying way of thinking about the path in between lines that will clearly demarcate and provide support to the underlying data points. And then we can then use this intuition of thinking about those support boundaries and try to see if you can either have a way in which you make sure that your data points are either all within those areas, is one way to think about. And the other way to think about is to make sure that your data points are all within the path. That's the flip of the same idea. So the one idea was to make the path is clear, and the other idea is to make the path fully populated. So that's how the underlying intuition will work in the upcoming discussions in this chapter. I'm clearing my markings and moving forward with my scroll, and you will see first illustration right there. And this is your linear SVM classification. So it is about classifying something A or B. It is not coming up with a number of regression number of the value. You're not actually coming up with a value in the first example, just classifying. And in that classification method, the way support vector machines basically work is to think about finding the widest possible street between classes. So you have class A, class B, and you find the widest possible street. That's the street width, which is wide and widest street that I can get to. And I have my data points. Some of them are here, and the other ones are here. And those circular ones and the crosses here on this side, and the circle ones on those side, A and B, 2 data points. And I'm trying to find the widest street in between these classes, so that I can use this concept of intuition to really get to the underlying way of thinking about SVM. That's how you should think about whether a data point is on the street. Like, is it here? Or maybe here, this A data point with crosses, is it here? Or is B data point here? And that is going to be on the street. This is my street. And so if it is on the street, that's one interpretation of some idea. And if it is off the street, meaning it is on this side or that side, so that's the other interpretation of the idea. And so you keep this idea in mind when we think about support vector machines, as we are basically creating ideas which are linearly separable from 2 sets like A and B, and then trying to find the widest possible street that separates the 2. That's the underlying intuition. And clearing my drawings now and proceeding forward. So that's how you think about why I call it SVM. So that's the idea about support vectors. These lines will help you support the data, keep them separate from each other in a way. Now, if you let's see if we can actually run the large margin classification in the example. So I'm running this notebook here. I'm running the setup steps. 1, 2, 3. And getting the large margin classification. We are again loading the same data set called iris for the flowers. Same thing. Again, loading the same one. And we are now coming at hold on, let me see what's going on here. So we are trying to draw these 2 pictures essentially in this segment with lots of plot functions. And let's draw them. So here we draw them. It is basically drawn. Now here you can see that it is trying to come up with a support boundaries of sorts based on petal length and petal width, two inputs, again petal length and petal width. Hold on, this is not petal width. I think this is just one of the classifications, just length only. And this is petal length, but what is this metric? It has to be width. So this is width. Okay, width. It's not written there, but it is width and petal length. With these two classifications, we have the blue dots indicating one type of flower, which is this versicolor, and the other dots are setosa. These small yellow dots are here. And you can see visually that the setosa flowers are actually very small apparently, and they are linearly separable by drawing a variety of different types of lines, as you can see. And so the underlying idea is, if you draw this line here all the way, and you try to find the widest possible street between the dashed line here and the dashed line here, that's the widest street we are looking at. And it is empty with no data points in there. So that's the underlying concept of creating this wide, large margin classification. Once we have a very, very wide separation of these two blue and yellow dots, then we can very effortlessly classify a flower into this one or that one, because we have a wide margin gap in between with a street in there. So that's how you look at from a graph perspective. Now, with this idea in our hand, we need to make sure that we scale these things correctly, because what happens is, if you have a illustration in which these boundaries are kind of skewed in a sense, it is already in a sense skewed. If you look at this picture, you will understand what I'm talking about. If you have some data points here that are like the blue, let me make it a little bigger. So I'm clearing my red ink again and making a little bigger to illustrate the point about the sensitivity of scale in SVM. I think that's something that really needs to be understood very clearly. So I am making my screen go wider so I can zoom in on the section that I want to focus on. And that's the idea that I want to talk about. So here is our red ink again. And in that red ink, what I'm trying to draw is, if you have a blue data point there and some other colored square, and this red dot or this square. So there is a dot and a dot and a square and a square. So it's a square, square, dot and dot. So now we try to draw the boundaries, and you notice that if you have such a data structure which is effectively not scaled properly, meaning that the lines that we have here and here are too close to each other, and that is a matter of fact because our data is not scaled. In that, we notice that most of our data points are in the segment of maybe this 80, and this is your 60, and this is your 50, and then we have here 20. And so the data ranges in between 60 and 50 are too close to each other. That's the reason why this road is not wide enough. And if you want to widen the road from a visual perspective, then it is important for us to scale on this axis. And scaling, basically, you will use the standard scalar method. And we already understand the scaling idea is basically you take every data point, you subtract from the mean, and divide by its standard deviation. That's what we are doing here. And we plot these metric numbers, same numbers basically, and we are doing the scaling to both this as well as this, both x1 and x0. And so that's the concept. In x1 scaling, it will translate to this. Basically the same 4 data points like before. Let me erase this. So drawing it again. The same 4 data points, they basically map one-on-one. But as you can see, visually scaled, they give us a lot more wider room to understand and interpret because of scaling. The scaling was x1 minus mean divided by standard deviation, and that function applies to this sheet of this row of numbers mapping to these row of numbers. And same thing done on x0. So like that. And so now you have 0 through 6 mapped on to a different scale. You will notice that the scale is at center point is a 0, 0 point. So this point is a 0, 0. And that is the nature of the beast, because we are subtracting the mean from the actual variable. And that's the reason why it is all 0, 0. And then we divide it by sigma, which is standard deviation of the items that we are dealing with, x0 or x1. And that's the reason why it gets scaled up. And the scaling is what you are looking at. We are using the standard scalar library, which I think is what you will see in the notebook also. So let me clear my drawings and close this one out, shrink the book a little bit. And okay, oh, hello, yeah. So that was the underlying idea behind scaling. And we will now execute the same things in our notebook right there. So the idea that we are really discussing is sensitivity to feature scales. And we are looking at these two pictures, and we will then also, I think that discussing two types of sensitivity: sensitivity to feature scale and sensitivity to outliers. That's also discussed here. And you will see both of them in illustrations. So let's go execute them in these two illustrations. So sensitivity to scaling features and sensitivity to outliers. Okay, I think I executed them. So now I'll go and discuss one at a time, beginning with our sensitivity to feature scales. What we're looking at, our data points that we saw in the picture here, the data, and we are calculating these numbers based on standard scaling. So you'll see some standard scaling apply. This fit action is basically before scaling, and then this fit action is after standard scalar. So this portion of plot is actually creating this picture, and this portion of plot is creating this picture. And what you now see is a wider street. We want a wider street because we can then very easily disambiguate between this side and that side, or this side and that side, because we want the street to be wide. The street becomes wider, relatively speaking, wider because of this idea, standard scaling. What it does, as you already know, is x variable minus mean divided by standard deviation of the ith. x0, x1, x1, like that. So it will calculate that and standardize the values and then do a fit transform, which will produce a slightly wider path or street. That's what we really want in a support vector machine. So SVMs are sensitive to, it expects scaling to happen. And so this is just generally done. By the way, this should be done in every case. Just use standard scalar left and right. It actually helps. It actually speeds up and improves accuracy and all that. So this is a good idea to just apply across the board, scaling. So clearing my drawings again and moving on to the next segment on the notebooks, which is about outlier, sensitivity to outlier. What you look at here is, again, the same idea, but we have an outlier data point. The data point is this one, which just doesn't fit. By the way, I mean, it doesn't belong there. It's an outlier. I'll tell you what when I get to the picture again. So let me, first of all, describe the idea that we are making a support vector machine fit on the data sets. We plot this, which is this representation. And then we do a, what is that? The other plot. This plot, the plot statements here will draw the other plot. And what they're really trying to point out is the sensitivity to outlier. And I'll read that a little bit. First of all, I need to clear my drawings and move a little bit up, scroll up. So I'm scrolling, and what you can see is if you have an outlier, which is represented by this little dot, it is impossible to actually draw a path or a street that will separate the two. And that is the challenge that we have. We have to have a scenario which, you have to handle the outlier, because if you keep the outlier there, then it really, really becomes hard to actually solve. This is actually impossible to solve, because you cannot draw two lines like these, for example, because you still have a wrong answer right there. That's an outlier. Now, that's an impossible scenario, cannot solve. The other scenario is solvable, but it actually deteriorates a whole lot. The quality of our output will be bad because of the narrow width here in between the rectangles and the circles. You see this outlier here? That is almost right there close to the blue guys. And we want that to be distinguishable, separable in a linear fashion by this black linear line with a wide margin classifier going. And that margin is not wide because this outlier is in the way. It is making that wide margin classification, which would otherwise look something like this, like a very, very wide margin, provided we don't have the outlier. So that's the sensitivity to outlier scenario that I am describing here, which is important in support vector machines. Just clarifying that. And so I'm clearing my illustrations and scrolling the book. And the other idea is what we have been discussing now up until now in these pictures and about scaling and about outliers is basically a black and white decision making. Is it that or this? So yes or no? It's basically binary. It is hard. It is hard in that its decision boundary is very hard. Meaning, if you are on that side, it is a absolute yes. If you are on that side, it is an absolute no with 100% guarantee. And that makes it a hard boundary. And we know it is nobody is here, none, they don't exist. And so these data points are either here or there. And so we can very easily and comfortably with guarantee say that no or yes, but depending on whatever we are classifying. That's a hard classification. But that is not always the case. Sometimes you have to handle softer classifications, and then basically it boils down to estimation of probability. Is it almost 99% no, or 1% maybe yes? That is a soft classification. When we boil down to probability of this being a no or a yes, then we are talking about soft classification. That margin that we are looking at, this path, is not a rigid boundary. It is a soft boundary now. So with that soft boundary in our hand, or that concept that we want to now discuss, I will erase my red ink and scroll. And what we really want to do in case of soft margin classification is basically come up with probabilistic numbers that will represent and represent the scenario where we can handle and come up with estimation of probability as to what a particular item is. Is it a yes or no? Is it that flower or this flower or some other type, some other object, some other classification? And that leads to a trade-off. The trade-off essentially is right here, which is you want to keep the street as wide as possible. And if that's the case, if you want to keep the street wide as possible, then you know what? You will draw the graph like this. And in the consequence, you will find this item, which is an outlier apparently, is going to cause a probability loss. So imagine here are some 10, say 39 dots of circle types. And this is one circle right there. And so if you draw a wide margin like this, and you end up with a soft classification, the chance of a number is somewhere here or wherever on the yellow side and not the blue side, will be something like 1 out of 40, because you have 39 dots here and 1 dot there. That's the estimation of probability I'm trying to give you an idea about. You're going to be wrong in 1 in 40 times. You will likely be wrong in estimations. because your estimation is to keep the margin, keep the street as wide as possible. And then what you have is a margin violation. This dude, the red dot, actually the yellow dot there, is a margin violation. And you want to minimize violations, but at the same time, you want to get as wide a street as possible. So that's a delicate balance right there. You cannot do both. I mean, you want to go as wide, then you actually end up with a narrow path like that. It's not wide enough. And then you have a situation which is a very strict margin violation policy, that nobody violates the margin. That's the road on which no circle or no rectangle will stand. The road is a clear path. That's hard margin. And when you're talking about hard, you're keeping your street narrow, especially when there is an outlier right there. And so what you did is you eliminated margin violation by keeping the street narrow. On the other hand, the flip of this is we already discussed, which is you keep the street wide, maybe go street like this, and then you have a 1 in 40 chance of being wrong in predictions. And that's your soft classification, which allows a limit, allows some margin violation, but then your street is wide, which is a trade-off. That's the balance in soft margin classification. That's what you're looking at. So let's now run some examples. So I'm clearing my screen again and see how this soft margin classification will help us understand the ideas better. So this is your first code in the example in chapter 5. Where is that? There it is. And there is your example. And what we are really doing in this example is we are again loading the same iris dataset and running our support vector machine algorithm on that. So here we go. So this is your run, and then a prediction. There we go. So run and prediction have finished. But let's understand what we just did. So what we are looking at is NumPy, import dataset, create a pipeline, standard scaler, linear SVC. So this is your support vector classifier. And just like classifier, there will be in the future down there somewhere, you will find support vector regressor. And this regressor will come up with a number or some numeric value of something, how many feet or how many, whatever, some number. That's the regression idea. And this right now is a classification idea. We are trying to classify, is it this flower or that flower? That's the SVC, linear SVC is your support vector machine classifier that we are loading the iris data set. We are again focusing only on the length and the width, not the other two, not sepal width, not sepal length, just these two. And then grabbing the data set in X and Y and putting a pipeline to first make it go through standard scaler and then running your linear SVC, which is your support vector classifier. And that will do a fit. And then we have the hyperparameters for SVC, outputted there. You can see various hyperparameters for the SVC, linear SV classifier. And then we are able to predict. What we are really providing it as an input is, imagine there's a 5.5 centimeter flower in length and a 1.7 width in centimeters. So that's the input. What flower would that be? And the answer is 1. What does that actually mean from a 1 perspective? It means it's actually giving us a prediction of some flower type. The flower type is 1. And our data structure actually is either a 0 or a 1 for Iris virginica. You can see in our Python the target value corresponding to number 2 with a double equal sign basically will generate a true value or a 1 value when it is virginica, the flower number 2. There are flower number 0 and 1 for those flowers. you will have a 0 or false in the Y matrix. So this 1 basically means a true, and true corresponds to Virginica, because this is actually number 2. That's the match right there. Target equals 2, meaning it's the Virginica flower for Y value for that data set. So with these inputs, the answer is yes, it's a Virginica, and that's your prediction. So now we generate the graph comparing different regularization settings. And we already know the idea of regularization essentially is to tone down the algorithm. If it is like going really aggressive and trying to fit every nook and corner of the data points, we try to regularize it. And I think this deserves a little bit of recap in terms of what we just discussed in terms of regularization. So if you have some data points here, those are red dots, and some other ones in, say, green dots. And now you are coming up with an algorithm that will try to fit that from a support vector classifier perspective. So you will have a blue boundary, and the blue boundary will try to draw something like this. Maybe it's just a linear class, right? So we'll just draw it like this. And that is a problem. The green spot came on the other side. So that's a problem. If we are dealing with soft classification, we have to understand that that's actually a violation. And so it is going to be within some margin. You will have a violation of the green dot that was there. Now, to regularize this idea, if you take this algorithm and apply a full SVM model, which is not linear, this is a straight line. And by the way, if you have a algorithm, same SVM algorithm, support vector machine classifier algorithm, if you apply that across a non-linear model, it will run in a fashion to actually go like this. Something like it will basically partition all the guys in a separate segment, and that's the green dots, and the others are red dots. And that is aggressively trying to find a boundary, going round and round, trying to basically fit the data to the extreme, and thereby coming up with an accurate, absolutely accurate decision boundary. And now you know what's a green and what's a red. Now, when you're doing it this way, it is basically leading to a scenario which is called overfitting, because it will not generalize to new data point. A new data point might pop up somewhere in let's say this other orange color. So a new data point here pops up, or maybe it pops up right there. What do you think will happen? Is it a red dot or is it a green dot? We don't know, and that's the challenge. We want to be able to generalize. The generalization will fail because this blue line actually is an overfitting scenario, and as you will see in more examples. So the underlying concept of regularization is to reduce the intensity with which this blue line is trying to fit the data as training data, so that it generalizes better. And what we are really into is to reduce the impact of the fit of the algorithm on the existing training data to some extent. And that we use a parameter. And that parameter is that you will see is a parameter called C here, that you will use to adjust the value of C, and it will respond with a, so like actually they tell you about this thing called hinge loss. So if you use the linear SVC class with a C equals 1 and the hinge loss function described shortly to detect Virginica flowers, the resulting model represented on 5.4, which is somewhere down. So I'll go to the picture again and clearing this up, going down. 5.4, where's the 5.4? I think that one. That was 5.4 up. Oh, I jumped. Apparently I jumped too much. Yeah, so this is your 5.4. Okay. So if you look at this piece of code, which is what we are going to execute now, let's clear that. and understand what it is going to do for us from a, is it the same one? No, I think we already ran this. Yeah, that the prediction was 1 for 5.5 and 1.7. We already ran this piece. And there are some other options in terms of regularization. It doesn't actually describe in this segment. I think this regularization idea is better handled when we are dealing with polynomial scenarios, basically nonlinear scenarios. That is almost coming up right there. So we have nonlinear SVM classifiers. And I think that regularization discussion will become much more intuitive once we deal with a nonlinear scenario, because it will straight away lead to what is called overfitting in some cases. And then you will see how adjusting the regularization parameters will help reduce the extent of overfitting. And to do that, I think we need to first discuss nonlinear techniques. So this idea that you're looking at in the picture that we have is actually just a representation of a data set, which is simply a single dimension data point. And I'll describe this picture for you so that you will understand and appreciate what we are really doing from a usage perspective. So let's go plot in blue in the red ink, with my red ink right there. So if you look at this picture in this sheet here, what we are really doing is specifically look at this segment. We have some squares and we have some triangles in between. The challenge with a single linearly separable SVM classifier is that it cannot simply classify. You have some data points that look like triangles there in the middle, and then we have some circles on this side and some circles on that side. How in the world can I draw a straight line to divide, you know what, everybody on this side is a square or a circle and that side is a triangle? I cannot just say it like that. That's a challenge. When you have just linear one-dimensional data set, you cannot really draw a point in between saying, you know, that's a decision boundary right there. And so what I'm really, it should be actually just a dot. So the decision boundary should be just a point. So that's my decision boundary. Anybody on this side is a circle and anybody on that side is a triangle. But what about these guys? That's a challenge. So that decision boundary that I had in a linearly separable fashion for a one-dimensional data set doesn't work. So if I have such a scenario, what I can do is, you know, use crafty math, literally math, to create a scenario which makes this data set linearly separable. And what needs to happen is, by the way, this picture is pretty much this picture. It's the same idea with a little bit more triangles in between. They have 5 and I have only 3. So just draw 2 more here. And so now that's the picture. Now, from a math perspective, what we will need to do is we will put this on a 2-dimensional. And so here is your X, and we'll artificially make stuff up, create a new Y variable out of thin air and label it as X square. Literally, that's the plan. And so we'll just come up with a new variable which is defined as X square, and that is what we will see as will help us in creating a linearly separable structure in a graph, which is going to be now in 2 dimensions. This will be one of the dimensions, and that will be the other dimension. So I'm erasing this drawing now, and now drawing the same thing in a different fashion. So here we are again. So we have a single dimension. We have the 0, which is where we have one of our data points, the triangle. We have a couple more here and a couple more here. These are triangles. Now, if I want to calculate, there are also these little squares, rather circles on the side. So what I want to now do is, for the x-axis, This is your negative x-axis. What we want to do is come up with a new artificially crafted y-axis, which has the representation of the squares of x. So basically, if this is your 4, then you have a new value corresponding to 16 right there. So you basically elevate this 4, this circle, from here up to 16 y, like that. You artificially elevate that data point in a 2-dimensional space. So you will move this one and put it right up on top there. This point happens to be on some number, say 2. Is it 2? No, not 2. Maybe it is 3. So you elevate this data point to a number called 9 somewhere here. And that y value is y equals 9 equals 3 square equals x square. So it's artificially lifting it up from the graph and putting it up on top. So what we will end up with is basically new plot that erases the old plot. We have these little triangles erased and the little squares also erased. And we will have these things sit something like this. You see, now we have, this is also your 9 and this is your 16 from a y perspective. This is some number called probably 8, maybe. What was that? 2, so 2, 4, it's 4. This is 4, this is 9. And so that's where we have our new items, a position of new items plotted on a y-axis, which is totally arbitrarily created based on this concept, x2 as x1 square as y. And with that, what we are really doing is crafting a new feature, crafting this new feature. And once we have that feature, our graph will look like this for the green, for the circles, and for the different ink for the other ones. Basically, it is a parabola now because of the square function. So with that parabola in our hand, we can now effortlessly separate the 2 data points with a straight line, pretty much like this. And that is our new street that we looked at before, right? This is our street, and it succinctly distinguishes between triangles, 5 of them, and your circles that were otherwise not really distinguishable early on with just 1 dimension. So we artificially crafted a new feature, x square, and then now we have a linearly separable data structure, primarily because we created it like this. And we call it x2, not actually y. It's just the orientation that I just use the label y, but y doesn't mean anything. It's actually x2. That's the x2 variable on the vertical axis. And this is your x1 as the horizontal axis. So we have now 2 features which are derivative. So this is the original feature x1 called x, and this is the new feature called x square. And this is a derivative feature, derivative. And with that derivative feature in our hand, we can now linearly separate these guys like this. So that's the underlying concept. We added a feature to the data set to make it linearly separable. And we play math tricks just like these in a variety of cases. The whole machine learning is math. So we will keep on playing math tricks like these as one example to come up with new ways to solve problems. And the problem here we are trying to solve is come up with a linearly separable method to separate these guys with the other guys. And that's what we did here and here and here. Linear separation. So now erase that and adjust the width. And go back to our sheet of notebook. and see if there is a code we can run, which is the polynomial regression, because now we are actually dealing with a polynomial. So now what we are going to do is still use the linear SVC model and standard scaler to conduct polynomial features. And what we want to do in our I think there's a new database here called Moons database. So this I think is Moons. So let's see where we can get to the right point. So there's a new database in use here in this example. And I want to just look at the database. This is the Moons data set. Test it on the Moons data set in figure 5.6. Where is figure 5.6? Right here. Is that 5.6? Yes. So this is your Moons data set. Let's load it up. It is available in scikit-learn as an example data set. So we will first of all go to that segment. Where is our Moons scenario? Let me just execute these guys first. So before I forget, 1, 2, 3, 4, 5, and then now comes non-linear regression, which is we just discussed this picture, which is to artificially create a second x2 and then separate them linearly. And now comes this idea in here, which is your number 13, which is where we are importing the Moons data set. Now this is just another data set available in scikit-learn. We are going to grab the data in X and Y, 100 samples, some noise, and then plot, define a plot function and then plot. The plot data set is the way will help us create this plot. And this data set has two axes, X1 and X2. And it has some blue squares and green triangles. That's what we got. That's the data set that we have. And it just helps us plot these two, X1 and X2. Now with that in hand, we'll proceed forward. The data set available to us. Now we will import and make a pipeline, use the polynomial feature and use 3 degrees as opposed to only 2, and see if we can use a polynomial method of making a linear SVC classifier fit the data. So let's go see that. And I'm going to use the red ink again. And what we are looking at here is the idea of, again, using the data set, importing pipeline, importing the pre-processing polynomial features, which we are going to actually use right there, 3 degrees of polynomials. And this will basically generate the polynomials for us, just like we did the x2 as a new variable defined based on input variable x1 square. Same idea applied, and this scikit-learn polynomial features library will do it for us in 3 degrees. So this was 2 degrees. We are also using the standard scaler, and then we are applying linear SVC, the support vector classifier. And we do a fit on the data. And let's execute that. So on the Moons data set, I am going to clear this ink and run this segment. So it did. Now I am plotting our predictions. So the predictions that we are really trying to come up with is to create this illustration that we have in the picture, which attempts to draw a line between the squares and the triangles. That's basically it. So let's see what it shows us. This is what it predicts as an output. If you here you see carefully, there are cases where we have violations. So if you look at that carefully, there is a green item right there, which is on the other side of the line. The line is this line all the way curving around. There is an item here which is almost on the boundary, maybe on this side or that side. We don't know yet exactly. By looking at the picture, we cannot tell. This is also a problem spot where we have the blue item on the other side. So that is something to keep track of. Is our prediction that we plotted our predictions on the polynomial classification that we did in a previous step. And the output turns out to be this chart, which seems to have a couple of errors. That's what we notice. And we go forward with it. And what you will see is that, yeah, they have the same picture like we had. So the same errors that we have. So basically the same idea. And what we are now dealing with is a 3-order polynomial feature, which basically leads to the complexity of the algorithm growing phenomenally. And that is something to understand, that there is this idea, which is, okay, where did I click again? No, did not. Okay, so the underlying concept, and that is what I'm going to describe, which is called a kernel trick. There's another trick here in place. And this trick, you will see this is where the trick is mentioned, but it is not explained right here. The trick is actually explained like maybe in the next chapter or somewhere down there in the book. The trick itself is mathematically daunting to look at. So you can of course take a look, but I would go with a word of caution. Is the math is so daunting that even the book's author is saying that it is likely to cause headache. Even the author is saying the same thing. It is complex math. So without going into that, unless you want to, you can. But without going into that intense math about the kernel trick, I will just give you the gist of it. What happens is when you are introducing this idea of x2 is x1 square, and we just did with just second order polynomial, like polynomial feature, or degree was 2. So d equals 2, second degree polynomial. But in the example we ran, the polynomial degree was 3. And so what ends up is called a combinatorial explosion in terms of number of things you are dealing with. Simply speaking, if you have like A, B, and C variables, then you will come up with something like, let's put it simple, A and B. So you have A square, then AB, and AB and B square, just 2 of them. Add more to it. Then you come up with A cube, B cube, C cube. Then you have A square B, AB square, A square C, AC square, and B square C, BC square. Then you have A, B, C, and you have then the 3 at a time, 2 at a time. So the combinations that we are dealing with are growing as long as you keep the degree equals 3. The number of types you can write all these different terms of math that will create your polynomial expression to evaluate will explode. That's, I think, very intuitively obvious by just looking at the difference between second order and third order polynomial differences. You can see that this thing goes on and on. And there is also a thing called 1, which is basically a to the power 0, b to the power 0, c to the power 0. And that is also one of the items here. And so this is what is an expression of a combinatorial explosion of parameters when you're dealing with a higher order polynomial. And scikit-learn will allow you to do that by using your polynomial feature set, like we just discussed in the example already, with d equals 3, a third degree polynomial. But there is a trick, and that trick is implemented in support vector machines, in that you get the benefit of actually going to a higher order polynomial without making your algorithm slow down and without making it deal with the combinatorial explosion of factors in your multi-order polynomial. In fact, you will have that complexity, but your SVM, support vector machine algorithms implemented in scikit-learn, is written using the kernel trick. What does it mean? It basically means you get the benefits without actually having to add higher degree polynomials like this. You get all the benefits without actually doing the combinatorial explosion. Without dealing with this, you still get the benefit in SVM. That's the trick. Now, it is mathematically involved exercise to just go through the math to understand what the trick is and why it is valid, and why there's a proof, by the way, available on Wikipedia. You can see that. But that's not the point. The point is this, that you get benefit without actually having to add polynomials for real. If you really add polynomials, you are running with just 3 degrees with these many variables and so many expressions, and you just make your math complex for no reason. It will slow you down. But if you use scikit-learn, it uses this trick which doesn't slow you down and still get the benefit without actually doing this thing. That's the trick. So now we'll use this trick a couple of times, and then eventually we'll also, in the book, it a little bit gives you a glimpse of the math. It doesn't prove the trick as to why the trick is valid, but there is a proof on Wikipedia if you're interested. So what the trick is essentially, let's go run the trick here. The trick is already implemented by the SVC class, the support vector classification technique. So that is already there. Now, having understood that piece, I will clear the ink and close this and go to the notebook where I will actually run the kernel trick which we are discussing right now. And so here, what we have in earlier step, we did a fit, we scaled, and then we ran a polynomial kernel with 3 degrees, and then we did a fit. Next step, we are doing a 100 polynomial kernel and fit. Let's go run it for the fun of it. So the 3 degree polynomial and 100 degree polynomial, let's go see how the two will compare side by side. So the picture already shows you that in the book. Let's go run a 100 degree polynomial and see how efficiently it actually produces the output. So I'm going to execute it right now. Here we go. It is finished already. And let's go plot the pictures. And you will now see the benefits of a higher order polynomial without actually going through the math needed to make it unnecessarily something missed. Okay, what was missed? I think I skipped something. Let's go back. Go back here. Moon data set. Okay, let's go run these guys. So Moon data set imported, predictions plotted, polynomial kernel run, and there it is. So yeah, we have the output now. Let's go back to the output and look at the picture here. In the picture, what we are looking at is the polynomial 100 degrees applied. Why? No, not here. This is not the 100 one. This is the 10 degree polynomial. This D is 10. Hold on, let me read this carefully. Degree is 10. Degree is 10 here. So this is labeled wrong, or I'm reading it wrong. But degree, it's a 10th order polynomial. The earlier was 3 degree polynomial. This is a 10 degree polynomial, not 100. So I think I should correct what I said before. This is not 100 degree. It's just a 10 degree, but still big enough. 10 is big enough as such. So we have two different plots. One is a 3rd degree polynomial, which we saw with some errors before. Like there's this error here. There's almost an error here. And now if you look at the other illustration with 10 degree polynomials, which also ran effortlessly without having to bog down our CPU, we see that the line is a little better than the other line here. This line, the decision boundary, is a little better, this one. There are apparently still some spots like on the line, almost on the line, maybe not. Maybe it's not visually clear, but we'll find out what that actually does to us. But let's go read what we have here. This label is questionable. I don't know why they're calling it 100, but we'll find that out later on. So maybe it is because of the coefficient 100 is why they are calling it. So they're executing a standard scalar in a pipeline followed by the SVM classifier with a polynomial kernel, 10 degrees, and 100 as a coefficient. And this, I think, is a regularization parameter. And this is also another regularization. It will adjust the extent of the waviness of this curve here, how wavy it is and how accommodating it is to these dots and these triangles and the squares. That's the nature of these parameters. They will help us in basically adjust the intensity at which it will attempt to accommodate every single dot available in the data set for training. And we need to, of course, keep track of how the algorithm generalizes to other data or new data. With that, these are plot functions that are plotting the two pictures here, one with 3 and one with 10 degrees. I'm going to erase the illustrations and move this on the side. Okay. Now, another math trick is coming up soon, which is called similarity function. And that's just another math tricks. So let's go see what that trick actually does in our, it's another transformation trick like we discussed before early on, which I think I just should draw it. So I'll draw it in my pen using red ink. There we go. So hold on, make some room here, and now draw. Okay, so like in the earlier discussion of arbitrarily coming up with a new feature called x1 square, you saw that we had some data points here and we wanted to just move them on a different axis, just not one linear one. I should call it x1, one dimension data. We transformed this data set, whatever we had, into a two-dimensional data set by creating a new axis which is containing the value x2, which is actually mathematically x1 square. So we did this transformation, and these data points that we had to begin with here, they all kind of lined up like this, because that's the nature of this function, square function, so parabola. And these data basically go away in the new scheme of things, because now we are dealing with a transformed data set with a artificially created function, that or rather artificially created feature called x2, which is a representation of x1 square. And now we have x2 and x1, two features, and we can do better things with a second order expression of this idea, which is basically extending into x square. So with that, like we did before, in this example, the idea is similarity. And that is conceptually the same idea here. Same thing, except the transformation happens in a slightly different fashion. The transformation function is a Gaussian RBF, which is radial basis function. That's the function. Now what this does, this radial basis function, it is basically a bell-shaped curve. So like this, and it has, it varies from 0, like on the other side, 0, basically just like bell shape. And at the top, it is a value of 1. And on the other end, it is also 0 again. That's how the nature of the bell shape is. So 0 on this side, 0 on that side, and a 1 at the middle, when your value is whatever that initial midpoint value. So that's the nature of this expression. Now what we will do is use this expression to transform our existing data set in another fashion. So I'm going to clear my drawings again and draw. So what we now have is just two data points, and those are, actually not two, the same data point like we had before. What we had before was, actually clear. What we had before was a triangle followed by, total of 5 triangles here and here, like that. And then we had like 2 circles here and 2 circles here. That was the data set we had to begin with. Now what I want to do is do another type of transformation, this time called the similarity transformation. And that's the similarity feature with the similarity function used as Gaussian RBF, which is this one. And that function, what I will do is it requires something like a landmark. So we have to come up with these landmarks. So what I will do is I'll come up with these almost arbitrary points to begin with, and we'll discuss as to why these landmarks are chosen. And we'll discuss also a generalized method of selecting landmarks also. But let's go pick some landmark here. The landmarks that I want you to think about are the points that I will actually first of all clear, and then adjust my screen a little bit to help us understand this idea of similarity is this picture. So the same data set that we have here, the little rectangle, the little triangles, 5 of them, these 5 triangles, 1, 2, 3, 4, and 5, and then those 2 here and 2 there. Those data points that we already know of. What we need to be doing now is assign landmarks. And these landmarks that I'm assigning are going to be at this point right there, and at that point right there, 2 landmarks. And then we'll try to calculate the similarity function against both these landmarks. These 2 landmarks are x2 and x3. So as opposed to we had the x2 before as x1 square. That was the old example. Now we are coming up with 2 variables, x2 and x3, as the similarity of each and every data point compared to these 2 landmarks. And that similarity function is basically this math. So you run that math and you find out how your data point is similar to this and to this. And now if you look at from this perspective, and I'll erase my clutter handwriting again and focus on the idea, which is if I want to plot this particular point, which is this dot, which corresponds to, erase, not that dot, but the other dot. If I want to plot this dot, which corresponds to the triangle, which is at x1, the value x1 is actually -1. If I take this value, x1 is -1, which is that dot right there, and I want to come up with similarity with this landmark and that landmark. What I'm going to do is use this transformation function to come up with the value assessments for those 2 values, for those 2 landmark values. And so what that translates to is basically me taking the value of x1, which is -1, and inputting that into this function right here, which basically translates to e to the power hold on, how are they doing the math? New features are at x2 e to the power, which is 0.74, and x3 is e to the power, which is 0.3. Now these calculations that they're doing are not super intuitively obvious to me, but apparently then what is I don't know why this math, but let's get back to that one later. So why this math? This is basically a representation of this function, e to the power minus y times, they're calculating the norm. Okay, the norm calculation, that's what's going on. So let me illustrate that idea. They're calculating the norm right there. You can see the norm here. So this is your norm calculation. And squaring it, that's this norm squared. And this gamma is a multiplier. They have chosen the gamma value to be 0.3. And then they are trying to come up with the value of x2 and x3 are the 2 new variables, just like we did x2 x2 as x1 square. In an earlier example, this time we are doing x2 as this function from landmark number 1 and x3 as that function, some function from landmark number 2. And that's this expression. So the landmark number 2, this number 2 basically comes from how far is the landmark from where you are. So this landmark is a distance of 2 away from you. So this is 1, this is 2. And that's the expression of -1 minus that landmark itself. That's your landmark. And so the distance between that position and the item itself, which is landmark, is at 1, and this is at -1. So this becomes -1 minus 1, which is -2, and you're taking a square of that. That makes it a 2 square, which is this 2 square, and gamma value is chosen to be 0.3, and that's the basis for this math. As a consequence of this expression evaluation for the data landmark chosen to be this, the answer comes out to be 0.3. And for that landmark, the distance between this point and that point is just 1. Therefore, this 1 square. And then the answer comes out to be 0.74. So the number is 0.74 for the other variable x2. And this value is x3. So now what we will do is eliminate x1 completely, like we did before. And we now have x2 and x3 as the representation. So we will plot this point, the original point under discussion, as that point right there. This is the point at the numbers that we have. So this is your 0.74 here, 0.74, and that is your 0.3. And so you plot this at that point again. I'm going to clear this drawing one more time to help you clearly understand what's going on in this transformation. So erasing now. The transformation is basically taking this point and putting it there in a x3, x2 graph, and taking each of these points just like that, calculating this math, which is based on this function, Gaussian RBF function, and transporting all these points like we did before on a square function. Now we are doing it in this similarity function on 2 landmarks. And those two, x3 and x2, will come up with a picture that will look like this, this, and this, and that, and these dots, wherever they are. And that also gives us a linearly separable method. And that is the underlying concept. So we have to basically come out with an idea where we have data that is not linearly separable. We apply some transformation, some silly math, sometimes x square math, sometimes more complex math like this, to come up with the idea of we call it similarity function. I think there is a meaning to it, and I'll describe to you why is it called similarity. The underlying idea is to basically estimate how this item is similar to that item, or the extent of similarity between this item and that item, how far they are from each other. And based on that, they will then apply the bell shape expression and then come up with the y and x value as a measure of similarity between x2 and x3, and then plot all these points again. So that's the transformation from a linear data into a 2-dimensional data on x2 and x3, at the same time eliminating x1. X1 is gone. You don't see it here in this picture. So that's the transformation. It's just math. So basically helping us transform to a new dimension of x2 and x3 that will allow us to linearly separate the data points. That's the point, is to linearly separate them. It tells you right here, as you can see now, the data points are linearly separable. Now with that, having understood from what we are really trying to accomplish is find a way to separate the two so we can make a decision, either this or that. Classification, that's the underlying idea. And we used landmarks. And so in general, the simplest approach is to create a landmark location of each and every instance in the data set. That's the simplest technique that that is recommended in scikit-learn. Now let's go proceed further, and I will clear this screen and adjust the width of my book a little bit. And go forward. So the similarity method, like we just discussed. The two methods we discussed are the squaring method and the similarity method, which is your Gaussian RBF function, that exponential math. Now that exponential math is implemented in scikit-learn like that. And you notice gamma function that we used gamma as 0.3 in the earlier example. That gamma parameter is basically a parameter to adjust and tweak the intensity of your algorithm. And that's this gamma here, chosen as 5. And there is another parameter that will help us and regularize our algorithms as we go along, is the C parameter here. And that is your technique for transformation of data to basically make them linearly separable. And let's go run this piece of code in the notebook. So I'm going to clear it up, close, and go to the notebook and find where they are using this Gaussian RBF function, which is right here. They're plotting the graphs that we just discussed. And this Gaussian RBF is basically the same calculation like we did manually. They have a gamma set to be 0.3. That's an expression chosen. You can tweak it, but it is chosen as 0.3 in this example. We'll go with that, and we'll execute this instruction set. And then we have a set of plots. The plots basically show you the transformation that we just saw happen, which is where this point ends up there, like that. And our x1 has gone. We don't use it anymore. We just use x2 and x3, because this is not going to be used. The new plot of data, which allows us to linearly separate, is what we intend to use. And with that, I will execute the next step. And in the next step, you will see that it is actually coming up with what I would call, what is it calculating here? Print phi. Phi is what? What is phi here? Oh, phi is the Gaussian function itself. So that's this phi. That is what is being estimated. And that is your phi values. And that is 0.74 and 0.3. The one we did that manually calculated that. The same expression is calculating here. And then we are applying your standard scalar and RBF kernel to fit the RBF kernel SVM classifier onto the same data set that we are dealing with. So we execute that step. And in the next step, what is going on is creating this picture to illustrate varying values of the hyperparameter. This will help us understand what does it mean by what is called regularization. So you will see the same set of pictures in the book also, which is what will help us understand where your gamma, this gamma, acts as a regularization hyperparameter. And so what we are really doing in this illustration is various values of gamma chosen to see how it impacts the prediction function for support vector machines using the RBF kernel, which is your similarity function applied to the transformation of the original data set like we saw before. So let's see how this gamma actually changes the SVM classifier itself, for which we need to execute that code and look at the picture. The picture should be available in the book already. So we'll just look at the picture in the book as well as execute. So the picture in the book shows you this, and we'll execute the same thing in the book, which is the same. Basically, that's how the picture is created based on this plot. And we'll just look at the plot. Here you see that there are, varying two changes to the gamma function. Like the first gamma value that we have is your 0.1. The second value is 5. There's the two gamma variables we have. There are two C variables, and the C parameter as well as the gamma parameter goes into the algorithm itself in the SVC RBF kernel. And those two are used for tweaking the regularization, which basically means the intensity of the fitting of the algorithm. Now, when your value of C is very, very low, which is a heavy amount of regularization, by the way, a low value of C means it is heavy regularized, which means the curviness or waviness of the lines that will separate one from the other will shrink. It will not be as wavy as you expect it to be. And that's what you actually see right here in this picture, where it is almost a straight line. You see that here your C value is 0.01 and the gamma value is also low. So together they make the separation line almost a straight line. If you tweak the gamma value to a little bit different, a higher number, the separation still misses out on a couple of these points here and here, but it's a decent classifier. It doesn't miss out on a whole lot. So these guys are all blue squares, and these are all green triangles on the wrong side of the classifier. This is your classification boundary. This is your new boundary with a different gamma and a C value. So those two parameters are being passed right there in the algorithm. And we are trying to draw 4 different charts for all these variations. Variations of C, C with a 001 versus 1000 C. So you will see the intensity of the waviness of the decision boundary to make the data clearly separable is what impacts. These numbers actually impact that ability, the gamma and the C. Let's look at these pictures carefully one more time. Your gamma value is 0.1, your C is 1000. Here also C 1000, and here your gamma is 5. You can see that this algorithm almost captures every single point. There is apparently no errors here. So this is a green item, that's a blue item right there, whereas there is kind of an error right there, and there is somewhat of an error here. So those 2 error points, apart from that, the classification is able to correctly detect the boundary of separation of the blues versus the greens in this selection choice. And that's the underlying concept of using these parameters in the example of support vector machines with RBF kernel to help you regularize the intensity by which you will apply the fit of that algorithm onto the existing data set. And that will let you basically tweak and tune your performance of the algorithm on other data points that will pop up when you want to predict. That's the underlying concept. Now we should also quickly take a look at the documentation on the RBF kernel and see what these parameters actually are referred to in the documentation itself. I'll just quickly Google for them and make sure that we are understanding clearly the RBF kernel and the hyperparameters associated with that. So we'll go sklearn RBF kernel, and it should pop us straight to the documentation where it will describe the gamma. This is not good enough. This is something else apparently. This is sklearn metrics pairwise RBF kernel, but I want support. I think my query was wrong. My Google query was not the right one. So let's go back. Google query should include SVM term. And now we should see that. And here is so gamma. It doesn't describe, the documentation doesn't describe these details. They don't tell me an English meaning behind the gamma and C. They just use the word gamma and C and play around with it, but without explaining what it is. I was expecting to read English meanings behind these things, but apparently I cannot find that. Whatever. If I find it, I'll tell you. I'm curious about every hyperparameter that we have. It has to have a meaning to it, or at least some intuition behind what it does. We already get that some sense of it from just looking at these pictures, that a larger value of C basically means more appropriate fit to the data. This is almost underfitting when you have a value of C like this and a value of gamma low. Both of these numbers low, meaning it is almost underfitting right there. And that is something that is the underlying concept of regularization, which basically helps us adjust between these 2 points. So from here to there, we can tweak our hyperparameter values, and there are more. Some algorithms have more, some have less, and whatever values you assign to these, like 0.1 or 0.001 or 1000, so that's what your pointer will slide on this line here between underfit and overfit. And that's the idea of regularization. When you want to regularize, you want to go either this direction or this direction. You want to adjust your hyperparameters of the underlying algorithm to get the right balance. It is always, at the end of the day, a delicate balance between what you want and what data you have that you're dealing with. That's the concept of regularization. Let's go forward. And I will close this one and see if I'm missing anything here. Probably not. So we're now changing the topics to regression as opposed to classification, which involves a little discussion. So we'll discuss those ideas right here. So the idea essentially is that up until now, we have been discussing classification, like, is it this or that? Which is to basically think of it like, if you have to classify something, then you want to draw a street which is as wide as possible, and to make sure that you get the largest, widest possible street, which is empty. So you want to get an empty street and widest possible empty street between the classes, like X and Y, A or B, yes or no, whatever classes you are classifying, you want to get that wide possible street, which is empty. And that's the idea behind classification. You want to get a largest possible empty street between classes. That's the idea of classification. We did that a couple of examples up till now in SVM, support vector machines. And now what we want to do is the other opposite of the same idea. Same idea, exactly the same street idea and everything, but we want to fit as many data points as possible on the street, like right there, which is the exact opposite of this idea. In this classification idea, we're trying to get an empty street. On the regression idea, we are trying to fit every single data point on the street, as many as possible. That's the distinction in the two. And they operate basically the same way. You're just reversing the objective, which is the underlying concept behind support vector machine regression versus classification. So with that understood, I will clear my illustrations and read ahead. In the picture that you are looking at, what we are really looking at is this expression here called x1, and we have some y values, and we have those dots all over the map. And what we are trying to draw is a road that will fit most of the dots, right? If you try to adjust the width of the road, you can do that. And that width is actually adjustable by a hyperparameter called epsilon. And that controls the street width. So if you have a larger epsilon, you have a wider street. If you have a smaller epsilon like this, then you get a narrow street, which still accommodates most of the points, but not all of them. There are some points that are still left out, but that's the nature of the epsilon hyperparameter. In the underlying idea is it controls the width of the street. That street we are looking at on the street. We want to get everybody on the street. So we want to tweak this epsilon hyperparameter to the extent that it brings almost everybody in the street, and and basically that will help us in estimating the value of a regression function. That's the underlying concept. But let's run some examples to see what it will do for us. So what I'm doing now is again erasing my annotations and going to the code portion where I will run it. So here we are going to run the, oh, I thought I cleared it. No, clear again. Okay, there we go. And then I want to run the regression portions. So we will execute these segments, but I just want to find out this piece of code, which is where we are. And I think it is like that one. The book doesn't describe some of these things here, like random state, for example. That is not in the book, but doesn't matter. That's just the seed to get repeatable results in regression. We are importing setting the seed value to 42, and then run that linear regression, linear SVR. This SVR stands for support vector regressor with an epsilon value of 1.5. And now we will do two different epsilon values, 1.5 and 0.5, and see what the differences would be from a picture perspective. And then we'll plot that picture that you already saw discussed briefly. I'll just run through the code that will help us draw these pictures, and you can see the impact of epsilon right there. Now, if you have a data set that is inherently quadratic in nature or multi-order polynomial in nature and not linear, not straight lines, then in that case, trying to fit something that is not a straight line and try to fit something that is not a straight line, you want to try to fit in a, so if you have data point that looks like this and you try to fit a straight line, it doesn't work. We already know that. So this next idea is about actually dealing with non-linear regression tasks. Non-linear tasks that will help us calculate if you have a data pattern that plots like this. We know it is not linear already by the look of it. And so if you try to fit in a straight line, it will fail. It is bound to fail because it doesn't actually meet the underlying concept of the data itself. It's a polynomial data. It's a second order polynomial by the look of it. It goes like this. And so it's a square function basically. So you cannot fit a straight line, which means you have to handle nonlinear regression in support vector machines, which basically means that you are not going to draw straight lines anymore, which means we have to use a polynomial kernel. And that's what this idea is coming up, in which we will use nonlinear kernel in the support vector machine regressor and see how it will help us in fitting a data set that is not linear, inherently not linear. And that is what we are going to run the code for. So let's go forward. I will, first of all, generate some random data set and use that random data set, which is by nature polynomial in its shape. And I'll describe what I mean by that right here. The data we are using in this example is a generated data set right there. Here. So what we are doing is creating 100 data points with random X values, but the Y values are not random strictly. They are not just random. They have some random input, but if you read this expression for Y, it will evaluate something like this. Y equals 0.2 plus X divided by 10 plus X squared divided by 2 plus random. That's how it will look like. You can see that this number 2, well, 0.2 is right there. This 0.1 is here. This 0.5 is here. And some random expression. And so that random basically is noise. So this is your noise. Otherwise, it will be a perfect shaped curve that will pop up. We don't want perfection. We want to introduce some noise in our generated data because that's the nature of the beast. If I am perfectly aligning with exactly what I have, like I just had this idea, so I can maybe plot this same concept on the graph and oops, clear, close, draw, and choose, and then plot the same concept again, y equals, and there is going to be 0.2 plus, what do we have? X divided by 10 plus, what do we have? And then we have X divided by 10, then we have X squared divided by 2. Okay, so here we got X squared divided by 2. So 1 by 2 times X square. And then plus. I think that captures it. So I will print it. So that's your graph. Now, if you attempt to draw, or rather come up with the Y values that match this exact expression that I plotted, then you will get points exactly on that line. Like here, you will get points just like that on the line, which is not what we want. So, oops, I just went away from the line, but that is me, not a machine. So yeah, the points I'm drawing right now, that's what you will get if you don't have the random portion. But I want to, get some semblance of data which has some noise built in. Otherwise, it's so mathematically accurate that I can just use this as my function, and the algorithm will detect that. By the way, if you have perfect data, it will detect exact parameters and come up with these expressions that will evaluate a 0.2 and a 0.1 and a 0.5, and it knows what to do with it. It'll exactly come up with that expression and be able to guess it accurately, like with mathematical precision, which is not the case of real world data. So in our data generation, what we are doing is introducing some noise. So that means our data points will be all over the map, but broadly speaking, representing this curve. That's what you see here. That's the data set we are now using. So I'm clearing this drawing again and getting rid of this solver and not save it. I'll just cancel it, minimize. And now run the code. So we'll generate this data set. We'll import the polynomial kernel and make a fit on the data set. Then we will run a second degree polynomial, which is what we attempted in the first run, and then change these hyperparameters. C equals 100, C equals 0.01, and epsilon value is the width of the street at 0.1. That's the value expression that we are going with. In earlier, here we had only C equal to 100. Now we are going to do with two examples of 0.01 and 100. So two different cases, and we'll plot them. And so when we do that, we get these two plots. Now, let's go understand what's going on under the hood here. So if you now carefully look at the plots themselves, you will find that the width is same, but the nature of, or rather the shape of the curve, like here, is the actual curve, which is, sorry, undo. This is the actual curve that we know of, but that is not the exact nature of the data set. The data set is random, as we already have introduced randomness in the data itself. That's why you have data points all over the map. So this expression here with C equals 100 is attempting to capture most of the data points within these boundaries here. Most of the points, not all of them, most of them. There are some points that fall outside, but in here, if you have a value of C lower, keeping everything else the same, the only changes are between this and here, you notice that the shape of the curve gets flatter and the width is the same, but it excludes a whole bunch of data points here, as well as here and here. These are excluded points, which are not exactly what we want. We want to cover as many points as we can grab in the street. That's the underlying idea, is to fit as many as we can in the street to help us match the pattern of the data from a mathematical perspective using this SVM algorithm, which will then help us with coming up with a regression prediction, meaning a value or a number or a real number, positive, negative, whatever the number is. That value, we can estimate that based on a new data input, because we now have a clear road or a street on which we know the data fits. Most of the data fit there. So any new number, we can just very reasonably come up with a prediction for what that value would be for the input provided. So that's the underlying concept here. I'm clearing the drawings that I have made in red ink and closing the annotation. So under the hood, there is some discussion I think we need to have, which is how does this thing work? And so let me see if I can pull up my notes on that. Okay. Okay. So here, the book is asking us to skip it. Yeah, here you can safely skip it, but no, you're not skipping. Not skipping. So I will actually help you understand under the hood what is going on in SVM.
All right, I'm game for it if you are.
Sorry, say again.
I'm game for it if you are. I'm up.
Now, if you want us to skip, I will skip, but
No,
not.
I'm good. Let's do it.
Oh, let's do it. Yep, yeah, let's understand. So the underlying idea, as you see in this graph here, it's actually a two-dimensional, or rather three-dimensional graph. And so the concept here is what we are really trying to do. Let's split this three-dimensional chart into actual 2 dimensions, but understanding that we have variables here, petal width and petal length. Again, focusing on the same data set called flowers. And if you now look at this picture, what we have is this function is the expression we will calculate, which is basically the width. So the notations that are used for support vector machines are slightly different by convention from other expressions that we have seen before. In earlier examples, like in linear regression, we use this method in which we just use theta 0, theta 1, theta 2, all the way to theta n. And then we had a theta transpose x as the expression evaluation to indicate this vector. But in case of SVM, the general convention is to use this b as the bias term or intercept term, and then use W1, W2 as the corresponding variables used. So that's the reason why we have this W transpose as opposed to theta transpose, because the notation is different. By convention, this is how people have been doing in the past, so that's what we know. Now this B corresponds to the same theta 0 that we had before, but that's just the idea. So that with that calculations or rather the notations understood, what we have here is a H function, which is basically the representation of this expression W transpose X plus B, which is this expression, basically same expression which annotates the value of H here. And now that's our decision function, whether it will help us decide whether it is this flower or that flower, or yes or no. That's the idea. So we'll take petal width and petal length and plot them. What you're now looking at is a decision boundary in three-dimensional space, which is the plane here, which is this one, and the other plane, which is that one. There are two planes here. There's one plane like that and the other plane that goes like this. So those two planes are actually intersecting at some point. And that line, actually it's not a point, it's a line. So the line of intersection is this line here. And that is your decision boundary. So in a three-dimensional space, what you're looking at is the decision boundary is actually a line that crosses, in which the two planes will cross each other. And that's what you're looking at in these two features, the petal width and petal length. I will clear now and scroll a little bit to read my notes ahead. And the underlying concept is to focus on the training objective, which is what we want to calculate in terms of the width function, like we have been talking about, width of the road, width of the street. How wide that street is going to be. Is it narrow or wider? That basically boils down to the slope of that curve. So the slope is a small slope like W1 here. The smaller slope, or the weight vector is smaller compared to this one is higher. You see the higher number W1 leads to a higher slope, which makes this narrow. And narrow means precise from a regression perspective. If you have something which is very narrow and you have all the data points sitting right there, it is easier to pinpoint an exact value because you are close and very, very precise, almost precise in estimating a regression value. So regression functions, when you have a narrow street, will make a more accurate prediction for a estimation of a regression calculation. And so that's the underlying concept behind your training objectives, is to come up with the minimum width street that fits all the data points that you have in a training set, as opposed to the other way around, which is you find the widest possible street that doesn't contain anybody. That's the two opposite ways of thinking from a classification versus regression. In here, our objective is to find that narrowest possible street, narrow, which will accommodate every single data point within that boundaries that we have, the decision boundaries, as opposed to the other classification technique is to find the widest road or street with a width that you have, which doesn't contain anything, so that we can very easily classify these black dots from crosses. And that's the classification way of thinking versus the way of thinking here in a regression scenario, is to minimize the width of the road while still getting most of the points on the road. And that will help us basically fit a data set that may look like these data points, and you will come up with some kind of a decision boundary that fits just like that, and it still accommodates all your points. And the road is narrow, which means it is more accurate in coming up with a regression estimation. That's the underlying idea behind the two techniques. I was not annotating apparently, so I wrote down on the book itself, but doesn't matter. So I will now scroll. So the idea that I just described above is basically the idea of soft margin objective, which is to minimize the slack and minimize the expression W transpose W. That's it's actually a double thing. You have to do two things together when you're doing a soft margin objective. The goal is to minimize a cost function. From a math perspective, you want to minimize this. Actually, annotate that. So let me draw this. So you want to minimize this piece and this piece, which means your cost function will look like A plus B, where B is this and A is that. And that's what you're looking at here, is your cost function, which has a W transpose W, which is basically the what is it called? Hold on. Clear. Scroll. There has to be a way to express that. What is this thing called? I think it is the cost function. So let's see that the two mathematical representation of cost functions between hard margin and a soft margin classifier. In a hard margin, the objective is to minimize this expression subject to these conditions. And that's the underlying idea behind me describing you these things, which is to keep the margin narrow versus wide in a classification versus regression scenario. Now, if you clear that and look at a soft margin classifier, which is the next idea, compared with what we are now looking at, is a different cost function, which needs to account for minimizing the slack and minimizing the weight itself. The two parameters together need to be minimized. So your algorithm that will operate will attempt to find the minima of this expression, and that will become your soft margin linear classifier. And that's the underlying math behind it. Let's go forward. Going ahead with this, what we now have is basically another math. Math will not stop here. And so that's the hard problem. The hard part is there is too much math. And in the book, they claim it is outside the scope of the book itself, which is fine. But I found out that there is this idea of quadratic programming, which is nicely described in Wikipedia. So let's go there and clear my drawing. Then I have a link for us to go. So that is, why is it not clicking? Clear. And it is not going to let me click on that. Okay, fine. I'll just search it. Quadratic programming. That should take us to Wikipedia right there. Now here you will find that there are a bunch of different mathematical optimizations method based on quadratic programming. And many companies have commercial as well as open source solutions to solve these things. And so those solvers are available. And here are some short list of solvers that will solve quadratic programming problems. Some of the well-known ones are right here. Mathematica, MATLAB. There are also a couple ones that you may have heard of before. GNU Octave. That's an open source library, which is basically implements this in open source. There is a Fortran R library available. So a bunch of different ways to get quadratic programming solved, which requires a solver. And that is what we are going to discuss in this segment. That is just another way of solving the hard margin and soft margin are both convex quadratic optimization problems with linear constraints. So what we saw here in this expression in there, as well as the one before that, this one, you want to minimize them. So these can be actually mathematically solved with a quadratic programming solver, which is what this equation is. And you can run that using those solvers, and the solver will come up with the actual expected answers. That's what our scikit-learn is, by the way, doing under the hood. And here is more math. And so this is now leading us to a kernel trick discussion. And this part of the math, and so the last time I was reading, it actually mentions starting to get a headache. It is perfectly normal. And so that is what we are going to get into the portion, which is the kernel trick, coming up soon. And I will recap what we discussed in the kernel trick, and I'll basically show you the underlying math. It is wickedly complex, as you will see. I'm clearing my drawings and scrolling forward to get to the point where we are talking about kernel trick right now. And so there is your essence of the kernel trick, and here is the underlying math. This is the headache function, by the way. The headache function looks like this. And what we are looking at, this calculates the bias term, headache function. So whatever we have is the bias term calculation. If you're starting, the book itself says starting to get a headache, it's perfectly normal. It's unfortunate side effect of the kernel trick. So that's the bias term calculated here with this math expression, and it does cause even me headache, but if you want us to go discuss this thing in detail, I will prepare for it and come and talk to you. I haven't actually studied this, by the way. I'll be honest. I have not studied this. That also, gave me headache. But if you want, I will discuss this. I'll study it on my own, and we will have a debate and discussion on what these things actually mean, if you're interested.
I'll be able to have much of a discussion on it, to tell you the truth.
So the bottom line is that the kernel trick is mathematically proved. And with that having proved, what these guys have done is implemented in the code for us in SVM, in support vector machine. So now if you look at this mathematical expression, which is kind of also complex, but let's go understand. This is easier to understand from an actual mechanics perspective. It is what is going on in this kernel trick. They keep talking about it. So let's go see here. The kernel trick for a second degree polynomial. Now here, we are calculating something using a second degree polynomial. So this is your expression in second degree, another second degree expression, and that evaluates to this. What does that mean? It means we can calculate the output without knowing what this phi is. You see that? If you look at this expression, you see that phi of A transpose times phi of B is A transpose times B square. There is no reference to phi here at all. That's the gist of this kernel trick, is that you don't have to worry about this transpose, the complex math, because you don't have to do it, because you can establish from a simple mathematical, not simple, you can establish from a mathematical derivation perspective that this is equal to this with no mention of a phi at all. That's the trick. That's really the trick. The essence of trick is right there. This is that this times this equals A transpose B square. You can just skip anything and everything to do with the phi, and phi is your polynomial explosion function basically. If you now look at what phi was, here it is. It tells you, suppose you want to run a second degree polynomial on the Moon's training set that we used before, and expression 5.8, which is this one, shows the second degree polynomial mapping function phi. So that's your second degree mapping function, which explodes like this, by the way. And so you have 3-degree polynomial, it will explode even further with so many different parameters to go with. And you can simplify that without knowing what this phi is, without knowing what that second degree polynomial transformation mapping is, you can just come up with the answer that you expect for the product. And that answer happens to be as simple as this, which has zero reference to phi. This is your phi. There is no reference here. So just simply A transpose B square. So if you want to calculate the phi x, if you want to do the math, you can do that simply by not doing it. That's the trick. And so you can see it ahead. If you remember this expression a little bit, here this one a little bit, you can now match it with the headache function a little ahead. We'll go there now. The headache function is basically a generalized representation of the square function, the second order polynomial. So here you see second order 5.8 right here, and now we will go to the multi-order. And this is your, where is that multi-order? Right there, making prediction with kernelized SVMs. That is phi, there is phi, but at the end there is no phi. So you want to calculate this parameter, and we don't have a phi at the end. Let's move forward. Well, yeah, I think this needs to be really understood. We have to have a separate discussion just on this kernel trick, but the essence of this kernel trick is right here. This is the essence. What is it? Let's read a portion of this. So you don't actually need to transform the training instances at all. Just replace the dot product by its square, and you're done. That's the underlying logic, or rather, that's the underlying idea behind the kernel trick. And that is implemented already. So we can actually use a multi-order polynomial without actually running that, because it doesn't even run it. It just does this transformation, like you see here. And a kernel is a function capable of computing the dot product of a phi dot another phi based only on the original vectors A and B without having to compute or even know about the transformation phi. If this phi transformation is like conceptually similar to this transformation of x transforms to x square, that becomes your x2, this was x1, that was one transformation. The other transformation example you saw was a similarity function, that we had some data points, we transformed them to a data point in a two-dimensional matrix with an x3 and an x2, and we excluded x1 altogether. So this transformation is conceptually the same idea. We are transforming phi. Phi can be whatever you want. I mean, you can choose what you want, but without even knowing about it, you can still get the result. And the result is as simple as this: A transpose times B and square. So just replace by the dot product by its square, like that. So you want to get a dot product, you just replace it by the square. So writing that again, we have a phi of xi transpose and a multiply by dot product of a phi of xj. If you want to get that, what you need to do is just ignore the phi and take xi transpose times xj and square it. You forget the phi and you get the answer. So this is basically equal. That expression is equal to that expression. And that is the underlying concept of the kernel trick. And with this, we are moving forward because it is headache function. Okay. Having said, I'm open to you. If you're interested, we'll discuss this later on after the boot camp, not right now. Let's keep forward.
Interesting, and it made me laugh.
I cannot hear you properly. I don't know why. Maybe.
It's interesting, and it made me laugh. Yeah, but we'll have to discuss it somewhere else. I'll have to think about it for a while.
Yeah, I know. We need to think and study and see if its value to really from a practice perspective. I think the value is not to a practitioner but to a researcher. So with that understanding, I want to skip it in the boot camp and not discuss like a researcher would, because I'm not a researcher and I don't want people to unnecessarily cause headache functions to cause them headaches. Because we are practitioners, we are actually using these things to apply to problems, and we're experimenting with a variety of data sets, and we'll bring up with our own data sets on the outside and use that. And especially when it comes to the idea of vision or maybe more examples, as you will see, I'll come up with that will help us understand and apply these things, as opposed to just getting down in the weed with headache functions, which doesn't get us anywhere, honestly. So I want to get to a result. I want to apply these to something that we can put to use, as opposed to researching why kernel trick works. We know it works. Other people have done the research, so we just use it. That's how I think about it. With that, let's go the next idea. The next idea is, again, I think this is one of the last few ideas in the support vector machine classifier techniques, and that is the idea of online SVM. The underlying concept is that, what an online technique is. When you get data and you get new data online, it basically means you're trying to learn incrementally. It is incremental learning is what is online learning. The phrase online basically means incrementally you learn. You get new data, you learn. And you get more new data, you learn again. And that's how you learn online. Your system is live, it is functional, and you get new data, you learn from it. That's online. And so in linear SVM classifiers, you can use the classic gradient descent method to minimize your cost function. So here, what you're looking at in this expression is a cost function, which is similar to what you saw before, but with a different expression right there. So you have the classic hard margin cost function, right? This one plus this segment. And that's your linear SVM classifier cost function. And the underlying concept, again, all the time when you hear the word cost function or the word loss function or any other such word, they all basically mean the same idea, which is I want to minimize the losses. I want to reduce my cost. So I want to find the minima or the global minima for the cost function. And that is what we will try. And so they will again apply the same concept of gradient descent to this function, the J function here, and try to find out the minimum point in this finding in the search for your global minimum for the bowl that we are dealing with. The bowl can be a multi-dimensional bowl or just a straight line like this, and you have a bowl, 2D bowl. So that's the underlying concept of a cost function that will help us calculate and come up with the minima. And you can, of course, use that use the gradient descent techniques to calculate the minima points. Now here, what is this? It's impossible. It is possible to implement online kernelized SVMs. However, these are implemented in MATLAB and C++, and for large-scale nonlinear problems, you want to actually consider neural networks instead. Of course, we are getting there soon. So soon we'll be getting to neural networks, which is going to help us understand. Neural networks is the TensorFlow library, basically, TensorFlow. And that's what we will get to, I think, in chapter number 9 when it starts. So we are dealing with chapter number 7 or 5. Exercises. So the idea of support vector machines. The next idea is decision trees. And we should actually, this is a net new topic. Maybe we should do this next time. But I'll give you a brief idea about what decision tree is and the underlying logic in this segment that will help you, understand some of the beginning concepts as we go into decision trees. Is the idea here. Let's see what a tree is. A tree is basically something that looks like this, and you have ground. And so you flip the tree around upside down, you have a root on the top. And then you have children or branches. And these branches can have children. And sometimes you have more children. So that's a generalized tree structure, like that. Now, if you're not dealing with multiple children, but you have a policy of having only 2 children at a time, that leads to a unique kind of tree. You know what that tree is called when you have only 2 kids? Do you know?
No.
Okay, so when you have a root and you have only 2 kids, it is called a binary tree. When you have two children. And so this binary tree concept is the dominant usage of trees. Most of the time that's the technique that people use. And this is actually a easy way to look at is what you're really doing is a decision-making function, yes or no. And then you go down and say yes or no. And you go down and say yes or no. And you go down again and say yes or no. Like that. You basically, based on some parameters here, some parameters here, you make that decision. Should I say yes or no? And yes or no? And yes or no? Is it a flower type A or flower type other? Is it A or no? Is it B or no? That's the classification idea going under the hood. And so this is a way to think about trees, is that you are basically creating a decision flowchart and using the representation of a tree structure to come up with a set of decisions you will make to assess or estimate whether something is this or not. So I'll just quickly show you a picture before I stop recording. And that picture is here. So here it's an quick example to discuss that. Is that you have a decision to be made at this point. You have a petal length less than equal to 2.45. And let's skip the Gini and other things later on. We'll discuss these later. And so now, class setosa, true or not? If it is less than 2.45, meaning it is the length of the petal is really small, we already know from the data set that it is a pure setosa flower. So if it is true, if this condition is true, then it is straight away this direction and you get the answer. And therefore, there are no children in the tree. It is a leaf. Root, leaf. No further kids. But on the other hand, on the other side, you find that this is actually more than 2.45. Then you don't go that direction, but you go this direction. And then you decide, what's the petal width? Is it more than 2.45? Yes. Okay, fine. Then you land up in this area. So now that was the length. Now you look at the width and you say, okay, tell me the width. Is it less than or equal to 1.75? Yes or no, or true or false. So if it is less than 1.75, then you go this direction and you end up with versicolor. Otherwise, no. That means it's a Virginica. So that is how you attempt to build a graph, or rather I should say a tree, a binary tree in this example, with only a certain number of depth. So the number of depth you have is 2. You're going 1 and 2 down, and then you stop, like right here. The purity is not 0. See that? Not 0, not 0. Here it is 0. It is absolutely accurately true that for sure this is setosa. But that is not the case here. So you may want to go further down and further refine exactly to get it to 0. But that's the next order of depth. You can keep going down the tree until you get the exact result you want. But that's the underlying logic behind decision tree in general. So we just discussed the brief idea of decision trees, which I just described to you. Now the underlying concept of a tree can be extended into a forest. And people just have fun with these ideas. The forest is basically what? It's a collection of trees. That's what a forest is. So you can have multiple children, and sometimes only 2 children, and you can have multiple trees like that. And this is a forest. And you can have random forests, and you will have fun with the tree and forest business. And so we'll discuss these next time. But I think the decision tree idea is a good one to think about. I think it is my favorite type of algorithm. Very, very useful. And in fact, if you recall, in our chapter number 2 that we did, our decision tree regressor perfectly actually overfit the data set for the retail, for the housing data set, right? Perfectly fitting the data and come up with a 0 error. That's this decision tree method. And so then we also evaluated another, I think it was a random forest regressor as opposed to a tree regressor. And that was the best promising output that we were able to come up with in our second chapter example exercises. So we did decision tree regressor, random forest regressor, and this was the promising one. This was overfitting, and the linear one was underfitting. So that's the same algorithm. We have run these things already ahead of in chapter 2, but now we are trying to understand what these things are. So that's what we will be doing, fun with trees the next time. And I'm stopping to record. So here we go.